जी अस्सलाम वालेकुम. Uh, Before going to the discussion of the switching power splice, I want to discuss in today's short video about the linear power splice. Linear power splice are very different from the switching power splice, and if you remember that about 2 decades or 3 decades before, the power supplies were very heavy as compared to today's adapters. Those early stage adapters were made up of a linear transformer, 50-60 hertz linear transformer, and the circuitry. So let's explore the linear power supplies first for today's. Linear power supplies consist of, as I told you, consist of a linear transformer, 50-60 hertz transformer, a heavy bulky transformer, and which step downs the input mains voltage to 20 volt to say 12 volt AC. And after that 12 volt AC, we use the silicon rectifiers to convert it into a pulsating DC. And after pulsating DC, we convert it to a full DC voltage by utilizing a capacitor. And if regulation is needed, tight regulation is needed, then we after that insert or install a regulator, normally series pass regulator. So these AC transformers were available in two configurations. In one configuration, the output secondary winding were made up of two wires coming out of the transformer, and for the other configuration there were three wires. For two wires configuration, the silicon rectifier can be connected in half wave configuration or full wave bridge configuration. And for the three wires configuration, the center wire is taken as grounded as ground, and the two other wires at their end is connected the two silicon rectifiers, and it is called the center taped full wave rectifier. Now as long as the peak inverse voltage of the rectifiers are concerned, they should be for half wave rectifier and full wave bridge rectifier. They should be of the maximum peak AC level voltage. They should withstand the maximum peak inverse voltage AC voltage. And for the center tape rectifier, these rectifiers should withstand twice the peak inverse voltage of the each secondary half winding. Then there is another important other than peak inverse voltage, there is another important parameter that is called the ripple factor. If we utilize only a transformer and the silicon rectifiers, then its output is a pulsating DC and not a pure DC. And the ripple factor, which determines what is the ratio of the AC voltage to DC voltage or AC current to DC current, that ripple factor for half wave rectifier is 121%, and for full wave rectifier, either center taped or full bridge, is 48%. In either case, the ripple factor is very much high and worst. I mean, for half wave 121%, and for full wave it is 48%. Whereas industry standard is that we should the output of the output of the power supply or power adapter should have ripple factor less than 6.5%. So in order to obtain the ripple factor of less than 6.5%, we utilize or insert the filter capacitors at its output, which converts this pulsating DC voltage to full pure DC smooth level. Uh, so then most of the time we need a regulated DC output voltage, because if we make a power supply which is made up of 50 hertz transformer and the silicon rectifiers, then and capacitor, then it is not a regulated DC voltage. As the load increases, the current increases and the voltage decreases, and so the ripple factor, which was less than 6.5%, again increases to the upper limit. So to overcome these problems, we utilize a regulator in regulator stage in between the output and the input of this filtered adapter. So or in other words, the regulator is basically a series pass element, which is normally made up of a linear configuration of a transistor. Uh, but the dissipation is very high, because suppose the output of the adapter is this adapter, which consists of the transformer and silicon rectifier and a capacitor, is 12 volt DC, and but we need a 5 volt DC output, 5 volt 1 ampere output. Then output the power would be 5 volt into 1 ampere, 5 watt, whereas to supply the 1 ampere current, the input voltage was 12 volt, so 12 volt into 1 ampere, 12 watt is being supplied. So the remaining of the power, which is the 7 watt, 12 minus 5 volt, 5 watt, which is a 7 watt, is dissipated inside the linear series pass element or the regulator. Or you calculate the efficiency, it is about 40-41%. But suppose another scenario in which the input DC voltage is 50 volt from this adapter, and we need a 5 volt 1 ampere output. Then again output power is a 5 watt, and but the for to supply 1 ampere, input power would be 50 volt into 1 ampere, 50 watt. So the remaining 45 watt will be dissipated in the series pass element or the regulator, and the efficiency in that case would be around 10 or 11%, which is very less. So you can see that linear power supplies are not much efficient, but in contrast the switching power supplies are very efficient, and their efficiency ranges from 70% to normally 85% or 95-97%. They are much efficient. But there is one as I have discussed with you the disadvantages of using the linear power supplies, and another disadvantage is that the components are bulky. 50 hertz transformer is bulky, filter capacitors are bulky, and heatsink is bulky. And MOSFETs or transistors, BJTs, they are also heavy duty. So there is one advantage, however, that the linear power supplies have low EMI spectrum. I mean electromagnetic interference is very less in case of linear power supplies, and also linear power supplies can have much less ripple, but nowadays switching power supplies are being used everywhere, and they utilize very light parts very small capacitor, inductor, transformer. Their size is very small, and even heatsink is also of much reduced size. And there is and also because they are being utilized in a huge quantity, they are also built in such a way that they qualify the electromagnetic compatibility specifications. And their ripple is also much better, if not best. And then there is another thing that I want to discuss, that as what is why the switching power supplies have the small components, small form factors. They have the very small components as compared to the linear counterpart. The main reason is that, the energy and power relation equation, that power is equal to energy into frequency. So to get the high amount of power from the same component, all we need to do is to increase the frequency, because as I discussed with you, that power is equal to energy into frequency. If you increase the frequency in 100 of kilowatts range, then the power from the same components can be obtained in of much high values. uh, then another thing that I want to discuss with you is the RMS voltage or the RMS current. Basically, or and your multimeters read the alternating voltage and current as the RMS. Uh, Basically, RMS voltage or RMS current are the produce the same heating effect as the DC voltage or current will produce. As an example, suppose that there is a heater of 1000 watt, and you attach it to the household supply, which is 220 volt AC, and for 10 minutes, and you measure the power dissipation and the heat it produce for the 10 minutes. And now you attach another heater to a variable DC power source, and increase its voltage to such a certain level that it also produces the same output power and for the same 10 minutes. And you will see that the surprisingly the DC voltage, if you measure with the voltmeter, it will measure it as 230 volt DC. So as long as heating effects or power effects are considered, the RMS voltage and current are same as the DC voltage and currents. This was a basic introduction of the linear power supply that I want to discuss with you. And in the coming videos we will switch to the switching power supplies discussion, and much of the important topics are there that I will convey to you. So stay connected, and thank you very much.